Hello and welcome to Six. I'm Norman Wildberger and this is an elementary course in pure mathematics meant for a very broad audience. In this, our second lecture in the course, we are going to continue with the basic organization of fundamental objects associated to six things. So let me remind you about the conventions that we've established so far. We've introduced, first of all, the nodes. And there are six of them, and they are the fundamental objects in the course. And these are the numbers 1, 2, 3, 4, 5, 6, arranged in this familiar order. From the nodes, we first then created edges. What is an edge? An edge is a two-set of nodes. That means it's a set consisting of exactly two nodes. And this is using the Wildberger convention for data structures where we do not use commas unless we intend to organize the elements of a data structure. So just having spaces alerts us to the fact that this is an unordered object. We can move these things around. That's a set. Now, instead of having to write all of this out every time we want to talk about a two-set, we shorten that by agreeing that we're going to represent this two-set with just the expression 1 followed by 2. In other words, we take the elements in the set and we put them together, but with the agreement that the smaller one in the ordering comes first. That way we get a canonical representative for every edge. And then here are the 15 edges from 1, 2 all the way to 5, 6. And then we introduced the idea of a meet. What was a meet? A meet was a two-set of non-incident edges. First of all, we say that two edges are incident, say like 2, 3, and 2, 4, when they share a node. While 1, 6, and 2, 4 are non-incident because they don't share a node, they don't overlap, they don't intersect as sets. So what a meet is a two-set of non-incident edges. For example, this thing here, this is a meet. It's a set. There's no commas, it's just a space between this object and this object. This object is itself an edge. This is another edge. The short forms for these things we've agreed are just 1, 2, and 3, 4. So another way of representing this meet in more compact form would be this. It's a set consisting of the edge 1, 2, and the edge 3, 4. And then we agree to further compress our notation to write it as 1, 2, 3, 4. And our convention here is that we're going to take these two edges and we're going to put the one that starts with the smaller number first. Okay. So we know these two edges by agreement are disjoint. That means they don't have any common nodes. So amongst the four, there's a smallest node in this ordering. In this case, 1. So we put the edge with the 1 to the left and the other edge to the right. When we do that, we get a canonical representative, a unique way of writing a given meet. Now notice that in this particular example, the two ingredient edges, 1, 2, and 3, 4, are both not incident with a unique other edge. There's another edge sort of off the page, which is the edge 5, 6. These two edges are not incident with 5, 6, and 5, 6 is the only edge that has that property. So in my first lecture, I gave you a homework exercise, which was to list all 45 meets, therefore verifying that there are indeed 45 of them, as I've claimed. Now, I'm going to present a solution to that homework, which maybe is the one that you've obtained, but maybe also different. I'm going to use that observation that we just made, that given any meet, there's a unique edge which does not overlap or is not incident with either of the edges contained in that given meet. So that means we can kind of organize all of the meets by the associated edges which are not contained in them. So we're going to do that by then listing the edges, and I'm going to reverse the order of the edges, starting with 5, 6, because that means that I end up listing the actual meets in maybe a more natural way. So what am I doing here? So associated to the edge 5, 6, I have 3 different meets. What are they? They are simply the meets involving the 4 nodes which do not appear in the edge 5, 6. In other words, the nodes 1, 2, 3, 4. Now, how many meets can we create from those 4 nodes? Well, there's exactly 3 of them. These 3 here. This is a very important point. If we have 4 objects and we're interested in grouping them into 2 groups of 2 each, like Spock, okay? There's a group of 2, there's a group of 2. That's one way of subdividing 4 objects into 2 groups or 2 sets of 2 elements each. And there's exactly 3 ways of doing that. 3 ways of grouping 4 objects into a pair of pairs. And we see that right here. The 4 meets are 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Once we've understood that, then it becomes almost completely clear how to organize these things. It becomes also clear why there are 45 of them. Because we know there are 15 edges. And what we're doing is we're associating 3 meets to every edge. So we're going to get 3 times 15, which is 45 meets. So for example, associated to the edge 4, 6, the other nodes not involved in that are 1, 2, 3, and 5. And here are the 3 meets that we can create from those 4 nodes. 1, 2, 3, 5, 1, 3, 2, 5, and 1, 5, 2, 3. You'd say, well, wait a minute, what about 2, 3, 1, 5? Like changing those things around. Well, we're not allowed to do that because we've agreed that when we represent this thing, the smallest node has to appear on the extreme left. Okay, so there's only a unique way of writing each one of these things. Okay, and then here is the list. You can check, hopefully, that I've got them all right. So for example, for 1, 4, the nodes not involved in 1 and 4 are 2, 3, 5, and 6. And here are the 3 meets created from them. 2, 3, 5, 6, 2, 5, 3, 6, and 2, 6, 3, 5. The 15 meets created from our 6 fundamental objects. Now I want to emphasize that the fundamental objects that we're dealing with and that we're constructing as we go are purely combinatorial. In essence, there's really no arithmetic involved, and in fact, no higher mathematics beyond really primary school familiarity with numbers and this basic idea of grouping things together in convenient ways. Nevertheless, as human beings, we often like to understand things using a visual representation. We are often quite comfortable once we have a visual representation of some abstract thing, because our brains have been biologically, oriented to processing visual information very well. So we're very good at that. And so it makes sense for us actually to try to find visual representations of mathematical situations. And we can do that here. And when we do that, you'll see perhaps why I've chosen some of the notation that I've chosen. Okay, because it's aligned with this geometrical manifestation of the theory I'm going to show you now. Okay, so let's work in the plane, which is very convenient for visual representation because we can draw it on a piece of paper and the 3-dimensional complexity is not there. So we're just working in the plane, and we start with our 6 nodes, which we represent as points on the page. 1, 2, 3, 4, 5, 6. And I've scattered them roughly around a kind of a circular region, but that's rather unnecessary. We could have put them anywhere. I just like it this way because it's sort of roughly symmetrical. But it shouldn't be thought of as a regular hexagon. It's just 6 points in the plane. And there are the nodes. Then what are the edges? Well, the edges are given by pairs of nodes, two set of nodes. For example, the two set 2, 3, or the edge 2, 3. That can be then represented by the line that is determined by the nodes 2 and 3, namely this one right here. So this line that I've drawn is a visual representation of what we called an edge. It's actually the edge, maybe I'll put it right here, 2, 3. Okay, that's the name for this edge. Now this is only one possible way of representing it. Maybe somebody else might say, oh, I don't want an entire line, I'll just do a line segment from 3 to 2. That would be another also valid representation of the edge 2, 3. Not quite as useful as this though. Okay, and so we could do that with lots of them. There's 2, 6. Okay, there is 1, 3. Maybe I'll put up here 1, 3. Okay, so we can see there's lots of edges, and can we count that there's actually 15 of them? Well, let's see. So through, say, this one here, we have 1, 2, 3, 4, 5. We have 5 lines passing through that one. And we can count, there's also 5 passing through that one, and 5 there, and 5 there, and 5 there, and 5 there. So altogether, if we count via the nodes, we get 6 times 5, or 30. But thinking about it for a second, we see that that counts a line twice. For example, this line here, 1, 3, will be counted once at the node 1, and also another time at the node 3. So we have to take that 30 and divide by 2 to get 15. So that sort of is a verification that we've got 15 lines without actually having to go through them. Although we could easily go through them also. Okay, what about meets? Well, as you may have guessed, there are some additional information on the diagram, namely these little black dots, which are meets of edges. So for example, this one right here, okay, is the meet of this edge 2, 6 and this edge 1, 3. It's actually a physical meet, like an intersection in geometry. So this is a representation of what we called a meet. Which meet is it? Well, we have line 1, 3, or the edge 1, 3, and the edge 2, 6. So the meet here is 1, 3, dot 2, 6. And we could easily give names to the other ones. For example, let's do this one here. Okay, it's passing through 4, 6 and 3, 5. So its name would be 3, 5, dot 4, 6. Now we said there should be 45 of those. Can we see 45 little black dots? No, we can't. And why not? Well, because some of them are going to be off the page. So for example, if you take this line here and this line here, in other words, the line 4, 5 and the line 3, 2, or I should say the edge 4, 5 and the edge 2, 3, then their meet is going to be up there somewhere. So we would have to extend the paper to be able to see the black dot that should be drawn there. Now, if some of the lines are almost parallel, like these two here are almost parallel, maybe, but maybe not quite, we might actually have to go quite far out in order to find the physical meet of those two edges or lines. In fact, we could see that if we had cooked things up so that two of these lines were exactly parallel, then we might have a little bit of a problem, because then the meet that we would like to draw would be actually very, very far away. In fact, it wouldn't exactly be on the page, even if we extended it arbitrarily. Suggesting that, in order to really make this kind of diagram work, we may have to go to something called projective geometry, which allows us to augment our understanding with points at infinity. And we'll be talking about that a little bit further on as we delve further into the course. But nevertheless, at this stage here, we see that we have a nice representation of nodes and edges and meets as geometrical objects in the plane. So we have this purely combinatorial description in terms of sets of things, and here's a corresponding geometrical visualization of that combinatorics. So while we have this picture here, perhaps it's a time to ask, well, what would be the sort of the next natural step for us to investigate? Maybe the geometry will naturally lead us to asking some decent questions as to what to study next, how to enlarge our landscape. So if we look at the story, we've talked about pairs of points, two sets, and two sets of two sets. What about taking three nodes? That's a kind of natural extension of looking at pairs of nodes. So for example, we could look at the set 2, 3, 4. That set of points. And how could we represent that set with a geometrical object? Well, one thing that is reasonably natural to do is to consider the triangle formed by those three nodes. This triangle right here. So that's a geometrical representation of the set consisting of 2, 4, and 3. As a set, it's unordered, so I don't have to worry about the order of the elements there. Okay, so that's a natural object. And once we've drawn that one, if we look back and say, well, actually, once we've singled out three nodes to form a triangle like this, then there's also kind of the opposite, or the remaining nodes. In this case, 1, 5, and 6. So they are also going to form a triangle which is in some sense disjoint from this one. It doesn't share any nodes. Let me just draw that also. Here's the triangle 5, 6, 1. Okay. That's the set 5, 6, 1. So when we're looking at triangles, it's not unreasonable to not just consider just single triangles, but also these pairs of triangles that seem to want to fit together. So that's actually a very natural and profitable kind of direction to think about. All right, so let's introduce triangles. So a triangle is a three set of nodes, and there's, I claim, 20 of them. Our notation is that, well, here's a three set consisting of the nodes 1, 2, and 3. And we're going to adopt a very similar notation as we did for edges. So instead of having to write these braces and these objects with spaces, we'll just put them together as 1, 2, 3 with the agreement that we're going to choose the ordering imposed by the natural order of our 6 objects. So the smallest one comes first, and then the next smallest one, and so on. That gives a canonical representation of our triangle. And how many triangles are there? Well, in combinatorics, this is a number called a combination. Okay? We're looking at how many ways we can choose 3 things from 6. So 6 choose 3. It's a binomial coefficient. And explicitly, as an expression involving natural numbers, it's 6 times 5 times 4 divided by 3 times 2 times 1. And this denominator 6 cancels with that 6, and we do indeed get 20. Now let me say a little bit about this formula in case it's maybe not familiar or you've forgotten it. Okay. So if we want to count triangles like this, the numerator and the denominator both have a meaning. Okay? The numerator is counting the number of 3-element lists, or 3 lists, that we can create from 6 things. Okay? So if we're creating a list like something like this, where there's actually a first object and a second object and a third object out of a total of 6, Then there's 6 choices for the first one, and once we've chosen that one, there's 5 objects remaining to be put in the second place, and after we've chosen that one, there's 4 objects remaining to be put in the third place. So that's altogether 6 times 5 times 4 possible 3 lists from 6 objects or nodes. Now, why do we divide by 3 times 2 times 1? Because that represents the number of ways of rearranging 3 things. Like once we have chosen 3 objects out of the 6, say objects 1, 2, and 3, then there's 6 possible ways of permuting them or rearranging them. In other words, when we write down all the lists created from 1, 2, 3, there's actually 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, and 3, 2, 1. There's 6 different lists that we could create from just those 3 nodes. And the number is 6 because, well, we've got 3 things, and we can put the first one, we have 3 possibilities for that. And then there's 2 possibilities for the second one, and then there's 1 possibility for the third. Okay. So this is why we have to take the number of 3 lists and we have to divide by the number of ways of rearranging any one of those lists to make an equivalent set. That's why this is the expression and why we do get 20. And we can verify that it's correct by listing them all. 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 2, 6. 1, 3, 4, 1, 3, 5, 1, 3, 6, 1, 4, 5, 1, 4, 6, 1, 5, 6. 2, 3, 4, 2, 3, 5, 2, 3, 6, 2, 4, 5, 2, 4, 6, 2, 5, 6, 3, 4, 5, 3, 4, 6, 3, 5, 6, and 4, 5, 6. And make sure that you agree that this is a very natural way of listing these 20 objects. In a way, it's like the mathematical equivalent of alphabetical order, lexicographical ordering in mathematics, where we sort of like count, but we increase the rightmost thing like a speedometer also. It's sort of like we're counting, and then once we've gotten to the max of that one, then we go back and we augment the next one to the left. Okay. So there are 20 triangles formed from our 6 nodes. A bit of additional notation. We'll say that, say, a triangle, say 1, 2, 3, is incident with the nodes 1, 2, and 3. And that it's also incident with the edges 1, 2, 1, 3, and 2, 3. So these are the nodes which are contained in this triangle, because after all, it's actually a set. Okay? And these are the 2 sets which are subsets of the set corresponding to this triangle. Triangle 1, 2, 3 is really the set consisting of the objects 1, 2, and 3. And this is really the set consisting of the objects 1, 2. So that's a subset of this set. So there's a natural association between a triangle and its 3 nodes and its 3 edges. Now if we have 2 different triangles, triangle here, triangle there, there's various relations that they can have. Okay? One relation, we could say that they're incident precisely when they share exactly 1 node. So geometrically, it's sort of like this. There's one triangle, there's another triangle, but they share a node like this. Okay? And we say that a pair, this is a different notation now, a pair is a 2 set of non-intersecting triangles. In other words, triangles which don't overlap at all, which share not just 1 node or even 2 nodes. They're completely disjoint, like the 2 triangles that I showed you in that diagram. So for example, here, the triangle 1, 2, 3, and together with the triangle 4, 5, 6. So here are 2 triangles. This is then a 2 set of triangles, and these are indeed non-intersecting because they don't overlap at all. There are no common nodes. And now, this is going to be quite an important object for us, a pair. So let's agree to have a short notation for it. we're going to do the same kind of thing that we did with meets. We're going to arrange the two triangles together with a dot separating them. But the triangle that's going to come first is the triangle that has the smallest node. Now, since we have two triangles, actually all 6 nodes are being used here, right? Because these are disjoint. So all 6 numbers are appearing here. So the number 1 has to appear somewhere. So in fact, this leftmost entry will necessarily be a 1. Okay? So the left triangle is the triangle that contains 1, and its entries are listed in ascending order. And then there's a dot, and then the other triangle whose nodes are also listed in ascending order, so that the 4 is the smallest one in that. So this is a canonical way of representing a pair. And a pair is a 2 set of non-intersecting triangles. So now we've introduced the idea of a pair. And I claim that there are, in fact, 10 pairs. That's maybe almost obvious because we've seen that there are 20 triangles. Okay, and each triangle has a unique other triangle which it's disjoint from. Okay, so those 2 triangles then together form a pair. So we're taking the 20 original triangles and grouping them into groups of 2. And so there's obviously going to be 10 such groups, 10 pairs. And here they are. 1, 2, 3, 4, 5, 6. 1, 2, 4, 3, 5, 6. 1, 2, 5, 3, 4, 6. 1, 2, 6, 3, 4, 5. 1, 3, 4, 2, 5, 6. 1, 3, 5, 2, 4, 6. 1, 3, 6, 2, 4, 5. 1, 4, 5, 2, 3, 6. 1, 4, 6, 2, 3, 5. And 1, 5, 6, 2, 3, 4. And I hope you'll see that this is sort of an obvious thing that I've done. I've just used this lexicographical orientation to organize things by sort of counting the first triangle successively, sort of from the smallest one all the way up to the biggest one, subject to the condition that it has to contain a 1. And then the rest is just the other nodes arranged in increasing order. So here are the 10 pairs that are now part of our landscape of 6. Now let's make another definition about 2 triangles. Okay, so if we had 2 triangles, we said that they were incident when they shared exactly a node. I now want to also introduce a second term that captures when they are sharing 2 nodes, like this. Let's say that 2 triangles are adjacent precisely when they share exactly 2 nodes. So let's think about triangles for a second. Here's a triangle, here's a second triangle. There's various relationships possible between these 2 triangles. They could be incident, they could be adjacent, or they could be in fact disjoint. There's 3 different possible relations between 2 different triangles. It's actually 4 relations if you include the possibility that they could actually be the same. Now for your homework, I want you to investigate the story with pairs. The story with pairs is in some sense more attractive than it is with triangles, because it turns out that any 2 of these pairs are related in exactly the same way as any other pair of pairs. Okay, so what's the homework? Show the following. So here's a statement. Given 2 pairs, each triangle in one is incident and adjacent with the other's triangles. And when I make a statement like this, I want you to think about justifying the statement or explaining why the statement is true. So I claim this is a true fact, and your job is to write out an explanation for the truth of this fact. What in mathematics we call a proof, okay? But it's just an explanation. So let me explain what's required here. It's actually not that hard, but it is a bit of a mouthful. So what we're saying is if we take two random triangles, say this one here and this one here, and we sort of look at how the triangles inside those pairs are related. So this one here contains two triangles, this one here contains two triangles. So if we look at, say, one of the triangles in this pair, say 1, 4, 6, its relation with this triangle is that it's incident because it has exactly one node in common. And with a relation with this triangle is that it's adjacent. It has exactly two nodes in common. And what I'm claiming is that that happens no matter which pair you take and no matter which triangles you look at. So the collection of pairs is somehow more symmetric than the collection of triangles. Okay, there's a richer symmetry here with all these pairs. That the connection between any two pairs is the same as the connection between any other two pairs. So I want you to write this thing down. So we've had some more objects to enrichen our landscape of 6. I'm Norman Wahlberger. Thanks for listening.